So far we've been studying line integrals of scalar functions. Every single line integral we've looked at, whether 2 variables or 3 variables, has involved a scalar function. And so our last kind of line integral is line integrals of vector fields. And this gets really interesting. There's a lot of really interesting theory around this, and we're going to get to explore it together. So let's set it up. Now, I'm going to intentionally not tell you whether your vector field spits out 2-dimensional vectors or 3-dimensional vectors. And likewise, I'm not going to limit C to being in the xy plane or a space curve. I'm going to leave it vague because it could be either one. When f is 2-dimensional, when f spits out 2-dimensional vectors, C is going to live in the xy plane. When f spits out 3-dimensional vectors, C is going to be a space curve. And I don't want to have to write this twice, so we're going to combine it. Okay, same general setup. You've got a function. This time it's a vector field, though, not a scalar function, and then a curve, which you've parameterized by r of t for t between a and b. Then we typically write the integral along c of big F, and then we write dot dr. And so this means the line integral of the vector field big F along C. That's how you read that. And how does one go about computing these? Well, you do very similar to what we've been doing. You take the line integral or the integral from a to b. You plug in the parameterization. We'll do examples in a minute. You plug in the parameterization, and then you dot with not the length of r prime anymore, but r prime of t dt. And I want to point out to you that dot really is the dot product here. That's important that we catch that. So that's how we're going to compute these things. I'm not going to get into sums and limits. It just wouldn't be helpful at this point in the conversation. I do want to show you some notation, though. Sometimes you'll see this written, and I want you to realize that when you see f dot t ds, it's the same as this. This is just a symbolic way of saying, hey, compute the line integral of f along c. This is actually the same thing. When you see this, it's saying compute the line integral of f along c. Now, some of you aren't going to like this because there's a ds at the end. Wait, what's that supposed to be about? Well, let's think about this notation, and I'll show you why it's actually the same, and you'll just need to recognize these mean the same thing. So let's think about what t is. Hopefully you remember t is the unit tangent vector, and so I can write this as the integral along c. Let's say, the integral from a to b of f of r of t. T is what? R prime of t divided by length of r prime of t. ds, you know, is length of r prime of t dt, and the idea is you can cancel those guys and you end up right back with where we started, f of r of t dot r prime of t dt. So please be aware that this notation, when you see a vector field dot with a unit tangent vector t and then a ds at the end, it's just the line integral of f along c. So this is just notation. Both of them mean that. That's how you do it. And okay, so before we end this video, let's ask ourselves, do line integrals of vector fields have any physical interpretation? You know, the first kind of line integrals of scalar functions, when your curve was lying in the xy plane and your scalar function was a function of 2 variables, we could interpret that as the area of a curvy fence. It turns out that they do. You can think about line integrals of vector fields as the work being done by the vector field f in moving a particle along c. I'm not going to get into the details of work. Those of you that have had engineering and physics, you'll know something about this typical definition of work. We're looking for total work done, so there's a sum, and everything works out really nicely. But I thought we'd just look at this. So here's a space curve, and here's a vector field. I've graphed this in Mathematica. And so the idea is this line integral of f along c is telling you how much work that the vector field is doing in moving your particle along C. And so right here, just ask yourself, is the vector field, is it helping C move, a particle move along C, or is it actually fighting against it? Is it helping it move, or is it hindering it? Well, it's pushing against it. So here, the work done by the vector field is actually negative. It's not helping you move. It's not giving you positive work moving you along. It's pushing against your space curve. And so here we can see that the line integral along C of f dot dr will be negative. It's actually going to do negative work. And if you're curious about that, I would encourage you to read the book, actually. It's got a nice, more details about work and how you can get this interpretation. One last remark, and then we'll do some examples. Orientation does matter for line integrals of vector fields. And so if you want to orient C the other way, then that you actually get out a negative. It just changes the sign of the integral. And I do want to go ahead and point out something to you. This notation right here, I can change my laser color. That's nice. And I can add a tail. Oh, man, I like this so much better. I just discovered this. Okay, so this notation right here might suggest that the orientation doesn't matter because you see an arc length symbol. Actually, it does, because when you change the orientation, you change t. It's actually, you've got a curve, and there's sort of two unit tangent vectors, and you end up with minus t, so the sign does change. So back to what we're saying. Let's go to red here, but I love that option to hold the tail. If you want to change the orientation of C on a line integral, then you just change the value of the integral. So we'll stop this video here, and in the next video we will work out some examples. We're actually getting pretty close to being done. You guys are going to make it. You're doing great.